We have misunderstood the universe. Pause on that for a second. That sentence didn't come from a conspiracy theorist or a science fiction writer. It came from a Nobel Prize-winning physicist, someone who has devoted decades of his life to measuring the very fabric of the cosmos. And he wasn't being poetic. He was staring at his own data and saying those words out loud, in public. Because the numbers don't lie, something doesn't add up. And after what the James Webb Space Telescope has shown us, the cracks in our understanding are no longer small enough to ignore. For close to 100 years, cosmology has operated on one foundational framework. Scientists call it the Standard Model. It's a collection of equations and assumptions that describes how the universe behaved from its very first fraction of a second all the way to the present day. And for decades, this model was extraordinary. It predicted things before we even had the tools to verify them. Observation after observation confirmed it. It felt almost too good, too precise, too elegant to be wrong. Then James Webb switched on. And what this telescope found wasn't a confirmation, it was a complication. In some cases, it was a direct contradiction. And the further Webb has looked into the deep universe, the wider these contradictions have grown. It starts with a single number called the Hubble constant. This number tells us one thing. How fast is the universe expanding right now? Not billions of years ago. Not in theory. Today, at this very moment, you'd think two separate scientific teams measuring the same universe would arrive at the same answer. That's the basic logic of science. Measure, verify, agree. They didn't agree. And this isn't new drama. The Hubble constant has been a battleground since the 1920s, when Edwin Hubble himself first tried to calculate it. His original number was so wrong that it made the universe appear younger than the Earth itself. For decades after that, two rival camps of astronomers fought bitterly over whether the true value was closer to 50 or 100. The disagreement was so intense it fractured the field. By the early 2000s, things had calmed down. Both camps landed somewhere around 70. The war seemed over. The number was settled. Except it wasn't. As instruments became more precise, a new disagreement emerged. Smaller in size, but far more stubborn. The first method looks deep into the past. The European Space Agency's Planck satellite spent over 4 years mapping something called the cosmic microwave background, the faint radiation glow left over from when the universe was roughly 380,000 years old. From that ancient signal, physicists extracted the conditions of the early universe, ran those conditions through the Standard Model, and projected forward 14 billion years. Their answer for today's expansion rate came out at roughly 67 kilometers per second per megaparsec. A megaparsec, for reference, is 26 million light-years. The result was precise, with a tiny margin of error and high confidence. The second method works in the opposite direction. Instead of modeling the past and projecting forward, it measures the present directly. A physicist named Adam Rees and his team developed what's called the cosmic distance ladder. They measure nearby pulsating stars called Cepheid variables, stars whose brightness fluctuates at a rate that directly reveals how luminous they truly are. Measure the pulse, calculate the true brightness, compare that to how bright the star appears from Earth, and you have a distance. From there, the team steps outward to more distant galaxies containing both Cepheids and a specific type of exploding star called a Type 1, a supernova. These explosions are useful because they all reach roughly the same peak brightness, making them reliable cosmic rulers. Combine the distances with how fast those galaxies are moving away, and you get the Hubble constant. Rees's team got 73, not 67, 73. That's a gap of about 6 kilometers per second per megaparsec. It doesn't sound like much. It is not small. In a field where measurements routinely land within 1% accuracy, an 8 or 9% discrepancy between two independent methods is enormous. It's the difference between a universe that's 8 billion years old and one that could be more than a billion years younger. It shifts the distances between galaxy clusters. It potentially changes the nature of the dark energy that has been accelerating the universe's expansion since the late 1990s. Think about that for a moment. If the universe is expanding faster than our best model predicts, everything that flows from that prediction shifts. The age of the universe changes, the timeline for when the first stars formed, when the first heavy elements were forged inside dying suns, when the conditions for planets, chemistry, And eventually life became possible. All of it moves. You're not adjusting a setting, you're redrawing the entire history of everything. For a while, scientists assumed one side had simply made a mistake. The leading theory was something called stellar crowding. Cepheid variables tend to live in the dense, dusty disks of younger galaxies. When the Hubble Space Telescope looked at them, its cameras sometimes blended together the light from nearby stars, making the Cepheids appear brighter than they actually were. Brighter Cepheids means shorter calculated distances. Shorter distances means a higher Hubble constant. The thinking was, point a sharper telescope at those same stars, clean up the blending, and the tension goes away. So Reese pointed James Webb at them. Webb sits 5 million kilometers from Earth, orbiting the Sun far beyond our planet's atmospheric interference. Its 5-meter gold-plated mirror collects infrared light with sensitivity that makes Hubble look like a pair of reading glasses. If any instrument on Earth or in orbit could resolve this debate, it was Webb. Many astronomers were already confident the tension would vanish. Some had basically written its obituary before the data came back. Webb's infrared cameras can cut through dust and stellar crowding with a precision Hubble never had. If the blending was inflating the Cepheid brightness, Webb would reveal it. The stars would appear dimmer, the distances would stretch, the Hubble constant would drop back towards 67. Crisis resolved. That is not what happened. Webb confirmed Hubble's measurements. Not roughly. Almost exactly. The Cepheids looked the same. The distances held. The expansion rate remained at 73. In early 2024, Reese and his team published a major paper announcing they had now verified Hubble's Cepheid measurements all the way out to a galaxy called NGC 5468, roughly 130 million light-years from Earth, across 1,000 Cepheids in 5 host galaxies and 8 supernovae. Their conclusion was unambiguous. Measurement error could be ruled out with very high confidence. Reese stated it plainly. With the known errors eliminated, what remains is the possibility that we have misunderstood the universe. At a physics conference in California, Reese once asked Nobel laureate David Gross whether scientists should start calling this discrepancy a problem. Gross told him no. Don't call it a tension. Don't call it a problem. Call it a crisis. The Hubble tension would be enough on its own. But Webb delivered a second shock almost immediately after it began operating. It found galaxies in the very early universe that had no right to be there. Not small, faint, primitive structures, which is what the standard model predicted at those cosmic distances. Massive ones. Galaxies seen as they existed just 500 to 700 million years after the Big Bang. Some of them comparable in mass to the Milky Way. A galaxy it took our own neighborhood 13 billion years to assemble had apparently pulled itself together in under a billion. An astronomer named Mike Boylan Colchin at the University of Texas ran the calculations and published his findings in Nature Astronomy. He showed that 6 of the earliest and most massive galaxy candidates Webb observed pushed right up against the absolute limit of what the standard model could allow. To form galaxies that heavy that fast, nearly every available atom in their surrounding dark matter halos would have had to convert into stars. In a normal universe, that conversion rate is around 10%. The other 90% of the gas never gets around to forming anything. It's too hot, it gets blown out by radiation, it simply drifts away. These galaxies seem to be running at 100% efficiency, like a factory that turns every scrap of raw material into a finished product with zero waste. Physics doesn't work that way, not in any model anyone had constructed. Then came a correction. A graduate student named Catherine Chwarowski, also at the University of Texas, led a study published in mid-2024 that re-examined the data. She found that many of the apparently overmassive galaxies were being deceived by their own black holes. These objects, nicknamed little red dots for their appearance through Webb's cameras, hosted black holes that were actively consuming enormous amounts of gas. The heat generated by all that infalling material radiated outward as light, enormous amounts of it, blending with the starlight of the galaxy itself. From billions of light years away, a galaxy with an extremely active black hole at its center looks almost identical to a galaxy with 10 times more stars. The telescope sees brightness, and brightness is usually a reliable indicator of mass. In these cases, the black hole was doing the work of billions of suns, inflating the galaxy's apparent size from the outside. Once those little red dots were removed from the sample, the remaining galaxies fit within the Standard Model's predictions. Jaworski's supervisor Stephen Finkelstein was direct about it. "There is no crisis in terms of the standard cosmological model," he said. "Not from the galaxies, at least." But the story didn't end there cleanly. Even after removing the contaminated data, roughly twice as many massive galaxies remained as the Standard Model expects. Not enough to break the model, enough to bend it. Jaworski suggested that stars may have formed more rapidly in the early universe than they do today, that the denser conditions after the Big Bang made it harder for gas to escape during star formation, allowing the process to accelerate. A reasonable explanation, but one that still requires revisions to how we think galaxies developed. In early 2025, Webb found something else. A massive spiral galaxy, quickly given the nickname the Big Wheel. That existed within the first 2 billion years of the universe. Spiral structure is not something that forms quickly. It requires relatively calm, orderly growth over long timescales. Not the chaotic, violent collisions you would expect in a young, turbulent universe. One of the astronomers who discovered it, Thamiya Nanayakata, at Swinburne University of Technology, noted that the galaxy either assembled its mass in an unusually organized way, or it formed most of its stars in place without the violent mergers that typically build structures of that scale. Either answer challenges the standard picture. Meanwhile, a separate team at Cambridge used Webb to analyze over 250 galaxies from that same era and found the opposite pattern. Most of them were chaotic, messy, clumpy systems that hadn't yet settled into smooth rotating disks. So the early universe contained both disordered infant galaxies and at least one remarkably mature spiral existing at the same time. That's not a pattern the Standard Model handles comfortably. And then there are the shapes. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo and including researchers from MIT, Harvard, and institutions in Taiwan, found that many young galaxies observed by Webb appear dramatically stretched, elongated like cosmic cigars. These elongated shapes don't match predictions from the cold dark matter model, which forms the backbone of standard cosmology. They do, however, match predictions from alternative frameworks, warm dark matter and wave dark matter, in which the large-scale filaments of the universe are smoother, allowing gas and stars to flow along them in elongated streams. That distinction matters more than it might seem. Cold dark matter isn't just one ingredient in the Standard Model, it's the scaffolding. It determines where galaxies form, how they cluster, what the large-scale structure of the universe looks like across its greatest distances. If dark matter particles are lighter or behave differently than the cold model assumes, the effects ripple through almost every prediction in cosmology. It would shift the expected distribution of smaller galaxies around larger ones, a distribution that has already been a source of tension for years. It would change how gravity bends light around massive objects. You cannot replace the foundation of a structure and expect everything built on top of it to stay in place. So where does all of this leave us? The Standard Model is not dead, not even close. It still explains the cosmic microwave background with extraordinary precision. It predicted the abundances of hydrogen and helium formed after the Big Bang. It accounts for how galaxies cluster across billions of light years. No competing framework can match its track record. But it is developing fractures that weren't visible a decade ago. The Hubble tension refuses to go away. The early universe is producing galaxies that are larger, more structured, and stranger than expected. The nature of dark matter, which makes up around 27% of everything that exists, may not be what we've been modeling for the past quarter century. And dark energy, the 68% of the universe responsible for its accelerating expansion, remains a placeholder name for something we cannot identify, measure directly, or explain. There is also a second, quieter tension that most people haven't heard about. It's called the S8 tension. It concerns how clumpy the universe is, how matter is distributed across space. The Standard Model predicts a certain level of clustering. When astronomers actually measure that clustering directly, they consistently find slightly less of it than the model expects. Rees has called it the quiet sibling of the Hubble tension. Less dramatic, but worth watching. If both tensions are real, they may be symptoms of the same underlying problem. Two cracks in the same wall. Not everyone believes the tension is real at all. Astronomer Wendy Friedman at the University of Chicago has spent years building an independent distance measurement method that relies less heavily on Cepheids. Her team uses additional types of stars found in less crowded regions of galaxies, which are less likely to be affected by dust and blending. Her 2024 web analysis produced 3 methods that gave different answers. 2 landed around 68 to 70, consistent with the standard model, while the Cepheid result came in near 72. Her overall combined result sits at roughly 70, somewhere between the two camps. Nobel laureate Saul Perlmutter, who reviewed her data, noted this might suggest a tension within the star-based measurements themselves before you even compare them to the background radiation. That's a different kind of problem. It means the distance ladder, the fundamental tool astronomers have used for a century to map the nearby universe, may have unresolved issues at its foundation. One idea that keeps surfacing as a potential explanation is called early dark energy, a hypothetical burst of extra expansion that occurred in the first few 100,000 years after the Big Bang and then disappeared. If something like that happened, it would shift the conditions of the early universe just enough to bring the two Hubble measurements into closer agreement without breaking everything else the model gets right. Cosmologist Mark Kamiankowski at Johns Hopkins, who helped develop this idea, has described it as the universe receiving an unexpected push right after its birth, a nudge that rippled forward through 14 billion years of expansion, slightly altering the rate we measure today. Nobody has detected early dark energy. But it remains one of the few proposals that could resolve the tension without dismantling everything else that works. New instruments are coming. NASA's Nancy Grace Roman Space Telescope will conduct wide-field surveys designed specifically to study dark energy. The European Space Agency's Euclid mission is already mapping the geometry of the universe on a scale never attempted before. Future data from the Gaia Space Telescope will allow astronomers to calibrate Cepheid distances with geometric precision, removing another potential source of error. And the Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made. We are living inside a question. The most precisely measured universe in human history is telling us two different things at the same time. And both of them appear to be correct. Somewhere in those 14 billion years we've never directly observed. Something is happening that we don't understand. Some ingredient we haven't identified. Some process we haven't modeled. Some property of spacetime we haven't yet imagined. Cosmology has been here before. In the 1990s, the field nearly collapsed under a different contradiction. Measurements suggesting the universe was younger than its oldest stars. That made no sense. Then came the discovery of dark energy and the accelerating expansion. And suddenly, everything snapped into focus. What looked like a fatal flaw turned out to be the shadow of something enormous that nobody had seen yet. That's what crises in physics actually are. They feel like endings. They almost always turn out to be doors. The universe isn't broken. Our map of it is incomplete. And the next version of that map, whenever it arrives, is going to be stranger and more remarkable than anything we've drawn so far. If this kind of deep exploration is what you're looking for, subscribe so you don't miss what's coming next. See you in the next one.